Welcome to this lecture. In the previous lectures, we have discussed about the MEMS micro machining technologies, where we studied about surface micro machining technology, bulk micro machining, and the Liga process. In this lecture, we will discuss about wafer bonding. In the previous lectures, we have discussed about many micro MEMS devices. In some devices, it's not possible to make the full devices in a single wafer. For example, you can see this is a MEMS pressure sensor where this is the input inlet, this is the diaphragm, that is piezo resistors, and this is the silicon other cover, this is outlet, all this. So this complete it's not possible to make this complete structure on a single wafer. So how this is manufactured? It's first built on a separate wafers, then they are bounded to make a complete unit. So here we understood why wafer bonding is necessary. The parts of a device is fabricated in different wafer and then combined at the wafer level by the bonding process. The wafer bonding ensures that the encapsulation is mechanically stable and hermetically sealed. These are the wafer bonding technologies. We can divide in two parts. One are the without interfacial layer, intermediate layer, and second is with intermediate layer. Without intermediate layer, there are two types: silicon direct bonding and anodic bonding. And other are adhesive, glass frit, and metallical may be divided again into solder and the eutectic. We will start with the direct bonding techniques. It's also known as fusion bonding. For this bonding, two ultra smooth that have the less than 10 angstrom roughness, that wafers are bounded without any adhesive or any applied external forces. Then how this bonding is done? First of all, surface preparation is done. It is clean, it make ultra smooth and the ultra clean with O2 plasma, hydration or the HF dipping. Then at room temperature, the contacting leads to the hydrogen bonding because of van der Waals forces. Means at the room temperature, both two wafers came into contact, and because of the van der Waals forces, hydrogen bonding will take place there. You can see in this first diagram, these are the two wafers and these are hydrogen bonding, they are H2O because of H2O. This is because of van der Waals forces. After that, annealing is done at about 600 to 1200 degrees centigrade temperature. That will convert this hydrogen bond into the covalent bond, that is Si2O bond. That will bring the bonds to the full strength. You can see these are the bonds, SiO, Si bonds. The advantages of direct bonding is that it's strong connections because of the covalent bonds are there. It's a relatively free choice of wafer material. We can use any wafer materials. New development in low temperature LTB process, bonding process, low temperature bonding, that is using plasma spin coating on the glasses can be used for low temperature bonding. Then it's a front end compatible process. It's a very fast process. Annealing can be done in the batch, so mass production may be done, and wide process windows are available. But some restrictions are the high demand of the wafer surface quality and the cleanliness. For this process, very high its quality means I've already told you that the roughness should be less than 10 angstrom. The surfaces should be very smooth and very clean. And second, the standard annealing, that is 600 to 1200 centigrade temperature we are using here, that is not good for CMOS production. That may damage the CMOS circuits. Next is the anodic bonding. Bonds an electron conducting material, silicon, to an ion conducting material, that is sodium glass, or known as Pyrex. You can see these two. This is the glass and this is the silicon wafer. They are used for bonding purpose. And a voltage about 200 to 200 to about 1500 volt is applied across these two plates, and the temperature is kept at 180 to 500 degrees centigrade, about 450 degrees centigrade, using this hot plate. When because of the high temperature and this potential, the oxygen ion from the glass will migrate into the silicon and form silicon dioxide layer between silicon and the glass, resulting in a strong and hermetic chemical bond. Again, it's a covalent bond, Si2. The advantages of anodic bonding are strong connection due to covalent bond, again, the wide process flow windows, most applied bond process, the wide application field in the MEMS is used. Disadvantages are limited materials like silicon glass only you can use, and formation of an oxide layer at interface may damage the electronics. In case of CMOS fabrication, it can't be used because SiO2 layers form between the two surfaces, two wafers. So for that purpose we can't use it for electronics circuits. Danger of wrap after bonding due to internal stress. SiO2 layer is built there, and because of that stress may be there, so there is danger of wrapping. Next is intermediate layer or assistant bonding. At intermediate layer, that is metal, polymer or solder glass, is used to facilitate the bonding between two wafers. These maybe metal may be used, polymer, solder or glass may be used for bonding purpose. We can divide it into three parts. The one is adhesive bonding, where we are using the polymer, epoxies and BCB are used. High strength we can got in this process, but low stress are obtained. These both are beneficial, but hermetic sealing is difficult to achieve. This is the disadvantage of this process. Next is the glass frit bonding, where using stencil process, a screen printed glass that is glass frit is designed on the wafer, meaning using a stencil process, screen printing process, a glass frit, a very thin film of glass is fabricated, built over the wafer surface. Then temperature of 350 to 450 degree, this glass is flow and it will create the hermetic sealing like in the previous one. So wide sealing layers is required, but problem is that for about 500 micrometer thickness layer is required for that glass film. You can see this one. These are the glass frit. These are designed by stencil or screen printing. So they will combine at this pressure. They will combine and make the bond. Third one is a metal layer bonding, where the pattern seal rings and the bond pads are designed using photolithography process on the wafers. A ring shape means for the complete ring shapes for rings for the wafer or the bond pads are just designed using photolithography process on the wafer surface. two types of bonding are there. One is solder bonding, second is the eutectic bonding. In solar bonding, the tin lead is used, or AU tin is used. That is these are the melting point for tin lead, that is 183 degree centigrade, and for AuSN this is 280 degree centigrade. The advantages are the low temperature process, can bond readily rough surfaces. If the surfaces are rough, in that case also this bonding is good. But wafers are just bonded at special points only, not complete layers are bonded there. So roughness can be ignored in that. Examples for this type of bondings are the BGA chip soldering on the PCB. That is also an example of this solder bonding, where there is a bond pads below the chip and they are soldered with the bond pads over the PCB layer. Next is eutectic bonding. In eutectic bonding done with the electroplated AU, other soft material, means here AU is electroplated over the wafer or other soft material is used. Then at the room temperature of about 300 degrees centigrade is used temperature, and the pressure required, that is 1 to 2 megapascal. That is the minimum. Can bore through the surface topography. Problem with this process that AU contamination was there in CMOS fabrication, and significant stress developed during the bonding because the high pressure is required, and because of AU layer there is a significant stress bonding there. Stress development is there. These are the references. Thank you.